So we've got a kinematics unit test coming up on Thursday. We're going to provide you with a little bit of an outline for that unit test right now. If you remember back, way back, beginning of September, just after Labor Day, over a month now, the very first thing we did was talked about the difference between a vector and a scalar. We all know that, right? Remember the difference between a vector and a scalar? A vector has both magnitude and direction. A scalar has only magnitude. Remember the vector cereal box that I showed you? Okay. Cornflakes tells you how much is in the box. Vector cereal tells us not only how much is in the box, but also the directions for eating it. Okay. Vectors have both magnitude and direction. So how do we know which quantities are vectors and which quantities are scalars? Well, largely you can remember which are vectors and which are scalars. But I'll give you a little cheat here. It's not really cheating because I'm giving it to you. If you ever forget whether something's a vector or a scalar, check your data sheet. Because a vector on your data sheet will be different than a scalar on your data sheet. How so? Yeah, it has a little half arrow over top of the vectors, whereas it doesn't have the little half arrow on top of the scalars. So don't forget that. Okay, if you don't remember whether a particular quantity is a vector or a scalar, check that data sheet, and your data sheet will tell you for you. Okay, some terms here. We have to know distance, position, displacement. These are all the terms that we learned on the first day, but there's going to be a couple additional ones that we learned later on. Time, speed, velocity. And then we'll add one more thing to that chart that we did first couple of days, acceleration. We have to know for all of those things, obviously the symbols for them. If we're going to use equations, we need to know the symbols for all of those different quantities. But we also need to know the units for them. The standard unit for distance, position, displacement are meters. The standard unit for time is seconds. For speed and velocity, it's meters per second. For acceleration, it's meters per second squared. Is it ever possible to use other units than that? Say, is it ever possible to use hours for time? Sure it is, sometimes. But if in doubt, then always go to your standard units of seconds for time. If you're trying to find the speed of a car, then kilometers per hour is a pretty standard unit, a pretty good unit. But if you're not sure, then go to meters per second, because sometimes you gotta use meters per second and seconds and meters and so on. You also have to know whether each of these are vectors or scalars, right? But again, if you're not sure, if you don't remember, then go to your data sheet. As long as you know what the symbol for these different quantities are, then you should be able to go back to your data sheet and determine whether it's a vector or scalar based on whether it has that half arrow over top of it or not. We learned 6 equations in this unit, and we got to be able to use all 6 equations in combination with each other sometimes. We've got our group A equations, or our group A equation, I should say. V is equal to delta D over delta T. That's valid only when we have a constant velocity. Remember that. If you're looking for a constant velocity, then use this equation. If not, then use your group B equations. Your group B equations consist of the basic acceleration equations, delta V over delta T, but also a bunch of other ones as well. D is equal to VIT plus 1/2 AT squared. They're all on your data sheet. You don't have to memorize them. You just have to be able to recognize which ones are valid and when. D is equal to VFT minus 1/2 AT squared. We don't use that one that often, but from time to time. VF squared is equal to VI squared plus 2AD. What's different about this equation? Solving for VF, what does VF stand for then? Final speed, yeah, not final velocity like it does in the other equations, final speed. And then finally, we've got D is equal to VI plus VF over 2 times T. We don't use this one a ton either, but we do from time to time. One of the mistakes that I find people make, a silly mistake that people make with that last equation that we wrote down, for whatever reason, people want to go VI minus VF. They get delta V confused or mixed into here somewhere. It's not VI minus VF. Delta V, the change in velocity, is final minus initial velocity. But that's not what we got here. Okay, VI plus VF divided by 2. So be aware of those equations. Know where to find them on your data sheet. They'll be on your data sheet for your test on Thursday. But also know how to use them, when we can use each one, okay, when each is appropriate, and how to rearrange them for whatever variable it is you're looking for. And the next thing we looked at, this isn't quite in the order. You guys have kind of summarizing here now, and sometimes when we do things in class, we can, after we're finished going over everything, we can put some things together. So everything's not quite in the same order as we did them in class. Next thing that I'm going to put down on the list, though, is graphs. And we did two kinds of graphs. There was position time graphs. And there was velocity time graphs. What do you got to know about those graphs? Well, we have to be able to recognize the shapes of them. So for instance, this particular shape represents a constant velocity. This particular shape represents an acceleration. This is a constant negative velocity, and so on. So we need to know the shapes of them. But we also have to be able to do calculations involving these graphs. What kind of calculations? Well, for position time graphs, we're going to have to find the position, up and over. We're going to have to find the displacement. The displacement is simply the change in position, so it's going to be up and over, and then subtract the two. The velocity, which is going to be just the slope of the graph. Or you could use V is equal to delta D over delta T. Right? Slope is rise over run. V is equal to delta D over delta T. The exact same thing, just two different ways of expressing it. Find the acceleration. And find the instantaneous velocity. Sometimes the instantaneous velocity is the exact same as the velocity if it's a straight line. But if it's a curved line, remember that you have to draw that tangent line, that line that skips through only that one point on the graph, and then take the slope of that line that goes through only that one point, the tangent line. For velocity time graphs, we have to find velocity, which is just up and over. We have to find the change in velocity, which is just up and over, and subtract the two. We have to find the acceleration, which is just the change in velocity over the time, or you could look at it as a slope, either way. This is the tough one right here, the displacement. The displacement is the area. So if you've got, listen, if you've got a nice easy shape like this, get the area, 1/2 base times height. But if you've got something like this, you got to break it up into two sections, the triangle and the rectangle. If it goes something like this, then it gets even more confusing because you got a triangle, you got a rectangle, another triangle, and another rectangle. Add them up. Okay, if something happens to be below the x-axis, like this, then just make sure it's a negative value. This would be positive, this would be negative values, add them up the same way. And finally, the last thing that we'd be asked to solve for with a velocity time graph would be the average velocity. And the average velocity is simply the displacement divided by the time. So whatever you get for the area divided by the time that's on the x-axis. Lewis, question? Good. Next, we talked about two-dimensional vectors. Sometimes we call them non-collinear vectors. We have to be able to draw vector diagrams. Remember, a vector, as you saw in the video just a few minutes ago, is a line with an arrow on the end of it. It shows both magnitude and direction. It's a line with an arrow on the end of it. Yep. Yep. No, that's a good question. If it's a curved line, you can't find the area, not easily. So I won't make you do that, no. Well, it is possible, but not in Physics 20, it's not. So we have to be able to draw vector diagrams, which remember the rule for that is make sure you draw them front to back. Right? You got the arrow, which is the front. You've got the tail of the next vector, which is the back. Make sure you draw one vector front to the next vector, back, except the resultant vector, which is the sum of all those vectors, the total of all of them. Make sure that you draw that start to finish. You have to be able to add them as well. So vector addition. You have to be able to do vector addition at right angles, which those are the easy ones, right? You get 90-degree angles then, and it's just two vectors, then easy, right? Just draw a triangle and do the Pythagorean theorem and the inverse tan function. If you've got more than two vectors at 90-degree angles, then do your x and y components, add up the x's, add up the y's, and then let's recombine them as a 90-degree vector diagram triangle. If you've got funny angles, though, we don't like funny angles. So what you got to do is get rid of the funny angles off to the side. Use sine and cosine to get rid of the funny angles, to get the x and the y components. Then add up all the x's and add up all the y's, and then draw your right angle triangle. Okay, the goal here, when you're adding vectors together, is to always get a right angle triangle. Sometimes we start that way. If it is, great. If we don't, then let's get there by adding my x components and my y components and resolving those funny angles if we have to. Next, we did relative motion. And navigation problems, right? The pilot aims or heads to the north. The captain of a ship heads directly west, but there's a river current of 10 meters per second to the south, and so on. Relative motion and navigation. This is the whole solid dotted line thing, right? If it contributes to where we actually go, then we're going to make it a solid line. If it is where we actually go, we make it a dotted line. So if it's the wind, that's not where we go. That contributes to where we go. Make that a dotted line. If it's where we aim, that's not where we go. Okay, that contributes to where we go. So we make that a solid line. If we're looking for the velocity relative to the ground, then that is the velocity that I actually go at. So that would become a dotted line. The mathematics of it is usually pretty easy. It's just a matter of getting that diagram drawn correctly. And then finally, boy, it's over already. Finally, we did projectile motion. And the projectile motion included two types of problems. The ones where we are launched horizontally, like Seth was in the quiz that we had today. Still not sure whether Seth was running off the edge of the building to get away from the girls or was pushed off the edge of the building by the girls. But nevertheless, he was launched horizontally. In that case, Vx is your entire velocity. There is no initial Vy. The other situation is maybe Seth joins a circus and becomes one of those guys that gets shot out of a cannon, flies off at a certain angle. When we have a certain angle that's, well, it's not straight across, we call that a funny angle. We don't like funny angles. So what do? We get rid of it. We resolve the funny angle. Seth was launched out of the cannon at 30 degrees at 10 meters per second. Then we would find out how much of that 10 was x and how much of it was y by using a little bit of trigonometry. And believe it or not, that's it. That's all we've done. It doesn't seem like that much, does it? Know about vectors and scalars. Know about all those terms. Know about the equations. When we talk about the group B equations, I'm going to put a little note in here, including gravity. It's general acceleration, but that general acceleration includes gravity when A would be negative 9.81 meters per second squared. Problems aren't any different. You just got to recognize that A in a gravity problem is negative 9.81. Know your graphs, position versus time, velocity versus time. Know what to do with those. Two-dimensional vectors. You'll be able to add the vectors together. And finally, projectile motion. Be able to solve both types of projectile motion problems, which we said, by the way, will appear as question number 1 on your exam at the end of the course, right? Projectile motion question. You know what? When you look at this list, you can probably be pretty confident that you're going to get 1 or more projectile motion questions on your test on Thursday as well, right? I don't think I'm going out going too far out on a limb here and telling you that you're going to get a projectile motion question or two on your test on Thursday. All right, does anybody have any questions? How do you guys feel about this test? Good? We'll give you that worksheet tomorrow when I'm not here to go over, and that'll give you a better idea as to how you feel on this test. Okay, work hard on that worksheet. Okay, really work hard on that worksheet. Work with each other, that's fine. Ask each other questions, but also ask me questions Thursday morning if you struggle with any of those questions on the worksheet tomorrow, okay? That is your test. If you can do that worksheet, you should be good for your test. If you can't do the worksheet, you might struggle with your test. Right? That's it.